Welcome all to the session 2 of Convergence, a peer learning initiative by our department. Let's begin with a silent prayer. Thank you. Today we have Nimmy Annie Matthew, our very vibrant and efficient senior of 2nd PG, to present the topic Exoplanets, an introduction to our neighbors. She did her graduation from St. Dominic's College, Kanyirapalli, and actively participates in all the activities of our department. I invite Nimmy Annie Thomas for the talk.
Yeah, let me share my screen first. Can you all see my screen now?
Yes.
Hello? Yeah, okay. Um, Good afternoon, everyone, and thank you, Genka, for such a kind introduction. Actually, I don't know most of you yet, but I'm nevertheless willing to bet that at some point in your life, you have been outside on a clear, dark night and looked up at the stars and wondered, do any of these stars have planets? Are there anything like the Earth? Are there any creatures on those planets looking back at me and wondering the same thing? It's this universal fascination with this question that helps to explain my today's topic, exoplanets, an introduction to our neighbors. So, exoplanets has got so much attraction both from scientists and from the general public. So, what I want to do today is to give a brief history of exoplanets from their discovery to the present. So, first of all, let me pause a moment for explain what exoplanets are. So, exoplanets are planets that are orbiting around stars other than our sun. For centuries, the only planetary system as we know of are our own solar system. But since in 1995, exoplanets came to the picture. So now we know of planets that are orbiting around stars other than our sun. So such planets are called exoplanets or extrasolar planets or exoplanetary systems. So here I'm showing you a plot. So on the horizontal axis, what I have given is the distance of the planet from the central star, which is given in astronomical units. So as you know, one astronomical unit is the distance of Earth from Sun. On the vertical axis, I have given the planet mass, which is in units of Earth mass. So of course, in one you can see the result. Also, I have shown the different planets in our solar system. The four terrestrial or rocky planets, Mercury, Mars, Venus, and Earth, and the two gas giants, Jupiter and Saturn, and the two ice giants, Uranus and Neptune. So the black dot here represents the first exoplanet, and it was discovered in 1995. So it is, as you can see, it is very much closer to its center star. See, the Earth is at one astronomical unit, and the Mercury is at. Hello? Hello? Hello?
Yes, Nimmy.
Am I?
We are
You're
able to hear.
audible.
Yeah, okay. Okay, see the Earth is at 1 astronomical unit and the Mercury is at 0.3 astronomical unit. So this exoplanet is very much closer to its central star. So this was the condition when the first exoplanet was discovered. Next, I'll show you the condition now. I'll just move back and forth between this. Quite surprising, right? So as you can see, most of this plane is being populated now. And the one thing you can notice is that 50% of exoplanets are being saturated within the orbit of Mercury, which means that most of the exoplanets are very much closer to their central stars. However, there are planets which are hundreds or thousands away from their central star. So this is going to be the story from the first exoplanet to over more than 4,000 exoplanets until now. And this is going to be the plan of my talk. So first, some of its. I'll be discussing the discovery and the technical challenges which were faced by the astronomers on that time and how they resolved all those technical challenges. Then I'll be discussing some of the recent detection techniques and the trends in exoplanet discoveries. At last, I'll be discussing some of the major conclusions that we have learned so far from these long years of exoplanet discovery research. So first about the discovery. 51 Pegasi b was the first exoplanet discovered orbiting around a solar type star, around a normal star. And for that discovery, it discovers Didier Close and Michel Mayer, the two Swiss astronomers, shared the Nobel Prize in Physics in the last year. So it is a star-hugging gas giant, also known as hot Jupiter, that takes only 4 days to complete one orbit. So that's going to be a year of 51 Pegasi b. See, the first exoplanet was discovered roughly 20-25 years ago, right? So what was happening since that time? Or how did they discover this? So they used a technique called radial velocity technique. And let me try to explain this to you. And radial velocity technique relies on the fact that the star doesn't remain stationary when it is orbited by a planet. So in fact, from Newtonian mechanics, we all know that both star and planet is moving about the center of mass of the system, right? See, the point here is that the star is also moving and we can make use of because the star is much bright, easier to detect, right? So I'll show you an animation. See, the planet is moving around the star and the star itself is moving. And when the star is moving, the spectral lines is when the star is moving towards us, the spectral lines is blue shifted. So you all have learned about Doppler shift, right? So the source emitting the light is moving with respect to us. The light emitted by the source will be shortened or lengthened depending upon whether the body is moving towards or away from the observer. So the Doppler shift is observed wavelength minus divided by the actual wavelength. So typically astronomers keep on measuring the spectral lines of different elements in stars. See, the star has different elements like hydrogen, helium, and many other heavy elements. So by doing the spectroscopy of these elements, they calculate the Doppler shift. So once you calculate this Doppler shift, you can calculate the radial velocity by using this equation. And this is what exactly Didier Close and Michel Mayer did in 1995. And they constructed this radial velocity curve. And from this curve, we can calculate the period of the planet and the maximum radial velocity, which is known as the radial velocity semi-amplitude. And if we know these two factors, we can calculate the mass of the planet by using this equation. So they found the mass of 51 Pegasi b to be about half the mass of Jupiter, and the period is about close to 4 days. This was a technically challenging discovery. That's why it took until 1995 to discover the first exoplanet. So let me show you how difficult it was to detect such a motion. Okay, so see, a Jupiter kind of planets around stars will produce a radial velocity semi-amplitude of approximately 12 meters per second. And to detect such a motion, we need a spectrograph of precision of 2 to 3 meters per second. But the typical precision of spectrographs used by astronomers have only a precision of 2 to 3 kilometers per second. So we need a precision of 2 to 3 meters per second. So most of the general purpose astronomical spectrographs are not this much stable. So the stability was the issue there. And to resolve or rectify this stability issue, they adopt two methods. The first one is the absorption cell spectrography to calibrate the spectrograph itself. So what we do here is that we just keep a gas of iodine or hydrogen fluoride at the entrance of the spectrograph, which will produce their own spectra, right? So when the starlight passes through these cell of gas, these lines will also suffer the exact shift so that we can calibrate it out. And the second method is the stabilized spectrographs. So here we decouple the spectrograph from the telescope and we'll keep it in a thermally stabilized room where we can control the temperature and pressure so that we can stabilize the spectrograph. So, okay, so this is how they rectify the technical challenge. So this assured the developments of exoplanet research from the emergence of astrophysics to the center. So this brought more and more people to work on this and discover new detection techniques. So these are some of such detection techniques, and among this, as you can see, its radial velocity and transit method accounts about 97% of exoplanet discoveries. So I'll spend quite a bit of time for explaining the transit method also. So basically, a transit method is used for measuring the radius of a planet. So here I'm showing a multi-planetary system, a star hosting more than one planet. So let us see what is happening. See, the planets are moving around the star. Okay. When the planet enters the line of sight or when it coincides with the star, so there will be a dip in the star brightness, a very small dip, but nevertheless a dip, right? So the larger planets will have a deeper dip when compared to the smaller ones. See, the light curve is a little bit complicated, but we have a sort of precision techniques to sort out this. So this is the technique. And as I was telling to you, transit depth is actually the ratio of radius, the radius of planets to the radius of star. So once you observe a planet through this radial velocity and transit method, we can calculate the mass of the planet, the orbital period of the planet, and the radius of the planet. And once you obtain this mass and radius, we can calculate the bulk density of the planet, right? So if you get just mass divided by 4 by 3 pi r cube. So if you get this bulk density can tell a lot about the planet properties. So here is the current census of exoplanet discoveries. So we have about 4,292 confirmed planets, and 724 of them are in multiple planetary systems, and over more than 5,000 exoplanets are yet to be confirmed. So this number is going to be increased in the coming years. So in this histogram, this red bar denotes the radial velocity method, and the green bar denotes the transit method. So as you can see, in the first decade, it was radial velocity technique was dominating. But around 2014 or 2015, transit methods start picking up. So once it starts picking up, it starts dominating, and its transit method is more popular. So that's all about the detection techniques. Now I'll be talking some of the major conclusions. So what exoplanet has taught from these long years of exoplanet research. Okay, the first one is that planetary systems found everywhere in the universe, which means that the planetary systems are quite common. The total occurrence rate is actually the ratio of number of planets divided by the number of stars surveyed. So it is approximately 1.3 planets per star. So on an average, there is more than one planet per each star, which implies that there are more planets than stars in the universe. And the next point is that there are more small planets than gas giants. And the third point is that there are more planets around cool stars than sun-like stars. So here is the graph of planet radius versus occurrence rate per 100 stars. So if the planet has 1 to 2 Earth radius, we call them as Earth. And if it is 2 to 4 radius, we call them as super Earth. And we have Neptune kind of planets and gas giants as well. So in fact, from this graph, we can see that super Earth kind of planets are more abundant than the gas giants. So which means that there are more small planets than the gas giants. So that's planetary systems are ubiquitous in the universe. And the second conclusion is that the solar system is an archetypal planetary system, which means that the exoplanetary systems which we have found so far looks entirely different from our solar system. Most of the planets are pretty close to their host stars. So because of that, the orbital period of planets are very small when compared to our solar system planets. So we can say that the architecture of most of the exoplanetary systems is found to be different from our solar system. So here is again the graph of planet radius versus number of planets. So I have given the planet radius in terms of Earth radius. So in Earth we can see there is Earth, and in 4 there is Neptune. So Neptune is 4 times larger than Earth. So you see the where the distribution is peaking. It's just peaking between Earth and Neptune, right? But we don't have such a planet in our solar system. After Earth is Neptune. No, right? So, but most of the exoplanetary systems we have found have this kind of distribution. So we can say that the solar system is not a representative exoplanetary system. And this is just to show you the diversity of planetary system we have. So this is TRAPPIST-1 system with 7 rocky planets around a very cool stars, and this star has got about hundreds of stellar mass. And you see, uh, the 7 rocky planets would fit within the orbit of Mars, right? So it is an extremely compact planetary system, which looks entirely different from our solar system. And the last conclusion is that the planet properties strongly depends on host star properties. So see, for a planet, we can measure its mass, its orbital period, and its bulk density, right? So for host star, we can measure its surface temperature. So if you look up at the night in the if you look up at the sky in the night, uh, you can see there are a lot of stars, and some of them are bluish in color, and some of them are reddish in color, right? So the hottest star will be bluish in color, and the cooler one will be reddish in color. So once you know the surface temperature of the star, we can have an idea about the mass of the star. So the hottest star will be more massive than the cooler ones. We can also say that the cooler stars host fewer giant planets but host more small planets than the sunlight stars. And the large and more massive planets are found to around metal-rich stars. So the stars having Jupiter kind of planet seems to have high metallicity. And so the planet properties are closely related to how much heavy elements are there in the host star. And so these are the main conclusions that we have arrived at. Okay, let me wind up my talk by quoting the words of Martin Rees, a famous astronomer. The study of exoplanets is perhaps the most vibrant field of astronomy. So there is going to be a lot of more surprises when we get a better and better look into these systems. So the field of exoplanet research is a matter of curiosity also. So that's all. Thank you so much for listening me patiently. Hello.
Hello. Thank you. It was really a very informative presentation. We were able to know about exoplanets, the technical challenges involved in their detection, its solutions, detection techniques, etc. Now we move on to the discussion part. If you have any doubt, you may either unmute and ask or drop your queries in the comment box.
അമ്മേ കഴിഞ്ഞു കേട്ടോ.
We have a question here. Which is the nearest exoplanet to our Earth?
It's Proxima Centauri b. It's about 4.2 light years away from us. Hello.
We are able to hear you, Chechi. Next question. Have any of these exoplanets showed life?
Um, Exoplanet seems to have the same, most of the exoplanets have different size. If giants have more lifespan than rocky planets, so that's it. Hello, the previous question was about the life habitability, right? Uh, Hello.
Yes.
I have mistaken that question. Still now we don't have any information about habitability of a planet. Uh, the still work in progress. So that's the question. So that's the answer. Sorry.
Okay. If you have any doubt, you may drop it in the comment box or unmute and ask.
Nimmy, which was the exoplanet very near to us? You were telling, I think I didn't hear that.
Proxima Centauri B is it's about 4.2 light years away from us. Proxima Centauri B.
But Proxima Centauri B, not the star Proxima Centauri. We
And
have a star, right?
nearest star,
Is
it's
it
Proxima
different?
Centauri.
Ah, yeah.
Nearest exoplanet is Proxima Centauri B.
B. Okay,
Longest
fine.
phase
Okay,
B is there.
okay. Thank you, Nimmy.
We have a question from Kartiga U. Mohan. Have you found water or air in any of these exoplanets?
No, we haven't found any traces of water, but we have found traces of phosphine on Venus atmosphere, so which is a biosignature, and that's
A question from Netra Shibi. Does the transit depth has any dependence on the distance of measurement?
um, not actually because yeah, in transit we are just measuring the luminosity of the star, right? So it just depends on the transition probability or transit duration, how long this transit will last. No, depends on distance of measurement.
Question from Priyanka Prasad. How many exoplanets have been discovered in 2020?
Okay. Sorry, I don't know the exact number in exoplanet discovered in 2020. I don't know the exact number. Sorry.
Nimmy, this was really a wonderful presentation. Nimmy. Really, you did a very great job. You did a good investigation. And then your presentation also was really wonderful. So congrats.
Thank you.
Yeah.
Miss, can we end the session?
Yeah, Ganga. If there are no more questions, you can end.
Hope there is no more question. So today we have come to the end of session 2 of Convergence. As you know, this is a peer learning group. We expect all your participation. If you are interested in doing a session, you may contact ASMI, our association secretary, or your concerned class teacher. Thank you for your presence, and I especially congratulate and thank Nimmy Chechi for her presentation. Thank you.